We could. Alrighty, let's do number or 12.14. Okay, so hopefully you guys remember that it's just going to be equal to the concentration of the products, okay, divided by the concentration of the reactants. Now, the important thing to note here is that we're not going to be doing one of the reactants, and that's H2O. And that's because, yeah, it's a pure liquid, and we ignore pure liquids and pure solids when we do the equilibrium constant expression, okay? That's it. That's 12.14. That's our review from last time. I didn't have to talk that much last time. I just needed to show you how to do this. All right, any questions? Okie dokes, let's move on. So now we're going to be actually putting numbers into this, the equilibrium constant expression. So fun. Okay, so we can actually measure the equilibrium constant of a reactant and product in a chemical reaction just by inserting the concentrations into the equilibrium constant expression. So let's take a look at 12.15. We'll do it together and I'll have you guys try one on your own, okay? So here it gives us this reaction and it gives us the equilibrium pressures for all the gases that are involved, okay? So same thing as before, we're going to be writing the equilibrium constant expression, so Kp, and then it's going to be the pressure of our products divided by the pressure of our reactants, okay? And since the coefficient is 3 here, we have to cube it, okay? So the pressure of H2, and we have to cube it. Okay, so all we got to do is plug in the values that we have, the equilibrium pressures for these gases. So if we look, let's start with the top. The pressure for ammonia is 0.166 atm divided by the pressure of nitrogen, which is 2.46. Going to multiply that for hydrogen, 7.38, and then you're going to cube it. Okay, so just to give you guys a little practice with the calculator, I'll give you a minute to punch it into the calculator and let's see what we get. Yes. Oh, thank you. Totally forgot about that. Appreciate it. Is that what you're going to tell me as well, Brendan? Yeah. Thank you. Sorry, guys. Will you forgive me? No, thank you. What are you talking about? I forgive you. That's the ultimate form of forgiveness. Exactly. Exactly. You do. I know. What would you guys do? I would like to know. You have a teacher that just emotionally and verbally abuses you all year, but at the end of the year gives you an A for no work. Would you take that? Oh. As tempting as that sounds, I can't do that. Because I'm on the record.
Are we gonna get extra credit?
Yes, we will have extra credit. I haven't decided yet. Oh God, like 400 points extra credit. Oh shoot, this is recorded. That's not on the record. You guys want more work at the end of the season? $200.
And then also, when are the unit 9 expressions due?
I'll do it end of the semester.
Oh, okay.
Yeah.
And then unit
Same thing. They can all be turned in at the end of the semester. Oh, thank you. You're my favorite student. But so is everybody else in this class. Because everybody is my favorite. But everyone is also my least favorite. Yeah. Yes. My affections for you are socialistic. Okay. All right, so you should have gotten 2.8 times 10 to the negative 5. Everybody good with that?
Yeah.
Okay. That's pretty much it. All you got to do is plug in the pressures and that gives the equilibrium constant. Okay, so I'll give you guys about 2 minutes to try it again. This time with 12.16, I'll let you guys try it on your own. Take about 2-3 minutes to solve this out. Check with the person next to you, and then we'll go over the answer in just a second, okay?
That's something to give us.
Cause I feel like it's really, like, we forgive you. We'll forgive you for an extra credit. Yeah. We forgive you for nothing. For nothing.
Oh.
We love you for.
I'm not for nothing.
We love you
All right, so moving on. Okay, so now that we learned how to write the equilibrium constant expression and to plug in the concentrations, we're gonna go more into, I guess, more experimental stuff. And this is the stuff that is what the majority of the AP test is going to talk about when it comes to equilibrium, okay? And it's something called an ICE table, okay? It has nothing to do with ICE. It's just an acronym, okay? So you guys don't need to write all this down. I'm going to show you guys how to use an ICE table, but I'll note the stuff that might be important, okay? So when we don't know the equilibrium concentration for everything in a mixture, we have to use an ICE table to figure out what the concentrations are at equilibrium, okay? So you guys might want to write this part down, but I in ICE stands for initial concentration. So basically, what is the concentration of your compounds at the very beginning? Okay, that's what the I in ICE stands for. Okay. C stands for how does the concentration of every compound change? Okay, so it's the change in concentration. All right, and a key thing to note about the change is it could either be positive or negative, just like all the other changes, okay? All right, and then the last one, E, is the concentration of each chemical at equilibrium. So this is where the concentration stops changing, okay? So ICE, initial, change, equilibrium, ICE. Okay, so those are the things I think are the most important to write down. Let me highlight it for you just so that you guys have it. But I'm going to show you guys how to use this table in just a second. All right, so there's a link right here if you guys want to go and read a longer description about the ICE table. You just really need to know how to use it. They're not going to ask you any questions about the ICE table itself. You're just going to have to use it in order to solve your problems. Okay. You guys ready to start? This is the big thing, and I think this is pretty much all we're going to be using for this unit. And next unit, we're going to be using this a lot as well. Okay, so let's take a look at 12.17. Now, we're looking at a fake reaction right now. That way, we're only working with one letter. Okay, but I want you guys to write down this equation right here. But I want you guys to make a little bit of space because we're going to be making our ICE table underneath. So you want to space it out. And then underneath the reaction, we're going to write ICE. And this is going to be our ICE table. It's going to look like this. Okay, so you're going to want to space that out a little bit. And we're going to be putting numbers inside of the ICE table. So make sure there's enough space to write in there. Okay. So I'll give you guys about a minute to make your ICE table, write the equation, and then I'll show you guys how to use the ICE table. Do you want extra credit for going? What do you mean? Oh, I wasn't planning on giving extra credit for the study-a-thon.
They're putting like big info on here. They said that you can get extra credit, you can retake tests, like, I don't know. if
Oh, I
the
think
teachers
some
are trying
teachers
to
are
get
offering it.
It's like-
But-
a teacher's like opted.
Yeah, it's an opt-in. It's not mandatory.
You should do that.
But then all.
I could do that. I could. Should is a very strong statement. It is. All right, so let's go into this problem. So we set up our ice table. Now we got to start filling in the info that we have. And what we do is we got to go through the problem, okay? So it tells us a sample consisting of 0.5 moles of X is placed into a system with a volume of 0.75 liters. Okay, so we'll stop right there. Don't fill in anything to the ice table. But basically what this is telling us is that we have a container, okay, and the volume of the container is 0.75 liters. What is that? Interesting. Okay, and then we put X into here. Okay, so we put X into this container and we put in 0.5 moles. Now, that means that we can fill in the initial box for X. Okay, now, one key thing I want to mention about the ice table is we are talking in terms of concentration. That means we're not doing moles, we're doing molarity. Okay, I know, very annoying. Okay, so what we're going to do is we're going to find the molarity of X in the very beginning. So molarity is moles divided by liters. So we're going to do 0.5 divided by 0.75. So the initial concentration of X is 0.6. Let's do 7. You could do 2/3 if you want to. But that's going to be extra work later. Okay, so 6, 7. If you want to be accurate, I think I said 3 numbers after the decimal point, you can, but it's not going to make a big difference. Okay, so far so good? Yes? Okay. All right, let's read the rest of the question. At equilibrium, the amount of sample X is known to be 0.35 moles. So what that's telling us is that as this compound sits in the container, it'll go to equilibrium, and at equilibrium, the equilibrium concentration will be 0.47. Okay, 0.47. Everybody see where we got those two numbers? Okay, so at the beginning, we start with 0.5 moles, and it's in a 0.75 liter container. And then at equilibrium, it goes to 0.35 moles, and it's still in the same container. So the volume doesn't change. Everybody good? Okay. Then it's asking us to find the Kc for the balanced equation. Now, I know it looks like, whoa, that's a lot of, so it's skipping a lot of steps, but it's doable with just these two numbers, okay? So the first thing we're going to do is let's fill out the top row, okay? So it tells us in the problem that we only start with X. So in the initial state, what is our concentration of Y and Z? Yeah, 0. There's nothing there, so we can just put 0. Beautiful. It only tells us there's X, so that means we don't have the other stuff. All right, now we're going to be going to the second row, and this is going to be the change. Now, this part's pretty easy, right? If we started with 0.67, and then we ended up with 0.47, what's the change? Yeah, 0.2. So positive. Oh, sorry, negative. Whoa, trip. Negative 0.2. Okay. I know you're about to say something. Oh, yeah. Yes, molarity. Okay, so far so good? All right. Now we can fill in the rest of this. But we need to look at the stoichiometry. Now, we got to look at the stoichiometry of the equation because it'll tell us how many moles or the molarity of X that's disappearing, but it also tell us the relationship to how these guys appear. Now, obviously, if this disappears, these guys are going to appear, right? So these are both going to have positive changes. So I'm going to put a plus sign just so I remember. It's going to be a positive change. Okay, but we need to know the stoichiometry. So if you take a look at the coefficient right here, okay, it's 2. Every time 2 moles of X disappears, you gain 3 and 4 of this. So what that means is 0.2 is equal to 2X, okay, the coefficient. Okay, that means for every mole that appears, it's going to be 0.1. Okay, so this is going to be equal to 2X. That makes sense. Two moles disappear, and that's going to total 0.2 molarity. Okay, now if we take a look at this right here, how many moles of Y are appearing? 3, yeah, so it's going to be plus 3X, which means that we're going to have a total of how much appearing? Yeah, 0.3. Okay, so far so good. Okay, same thing here. We're going to have 4X appearing, which is going to be obviously 0.4.
Wait, why is it 4x?
Because of this coefficient in the front. Yeah. So 2 moles disappear, right? 2 moles disappear. 3 moles appear, so that's 3X. And then 4 moles appear, which is 4X. Okay, now we can fill out the bottom row. So this should be pretty easy. If we go from 0 and we gain 0.3 molarity, what's the equilibrium concentration? Yeah, 0.3. And then here, obviously, it's going to be 0.4. Okay. Any questions about that? Pretty simple. Okay, so all we got to do now is finish the problem, find the Kc. Now, the Kc is exactly the same thing that we've been doing. It's the concentration of Y to the power of 3, concentration of Z to the power of 4, divided by the concentration of X to the power of 2. And remember, Kc is always talking about the system at equilibrium. So we're going to be using this final row right here, the equilibrium concentrations. And that's how you can use an ice table to figure out what the equilibrium constant is. So I'll give you guys a couple minutes. I'll give you guys 2 minutes to finish solving that out. And then we will go over the answer together. And then we'll move on to more ice tables, and then more ice tables, and then more ice tables. Alrighty, so let's move on to the next one. I'm going to see if you guys can try this one on your own. So this one's actually a little bit easier because you start in molarity. Okay, you don't need to do the whole conversion and whatever. Okay, so I'll give you guys about 5 minutes. See if you guys can set up your ice table. I want to make sure that you guys are able to plug everything in on your own and get the output. So I'll give you guys about 5 minutes to try that out, and then we'll go over the answer together. Okay, so for this one, you guys should have something like this to start off with. This is just what's in the problem. Okay. All right, so one thing that we should notice is by looking at the stoichiometry, you can see that the change here is going to be plus X, and here is going to be minus 2X, just based on the stoichiometry. And by X, I just mean the factor in which it'll disappear. Okay, now we know that here, HI goes from 0 to, oh wait, sorry, I did it the wrong way. Boop, boop. My bad. Getting my positives and negatives messed up right now. Okay, since you're gaining, that's why it's positive. And we can see that it goes from 0 to 1.87 times 10 to the negative 3. So that means that 2X is equal to 1.87 times 10 to the negative 3. Everybody good with that? Okay, because we go from 0 to that, we gain that much. And if we gain a stoichiometric factor of 2, it's going to be 2X. Okay, so that means that X is going to be equal to 0. Damn, I can't write today. Okay, 0.955, and I'm keeping it times 10 to the negative 3. If you have it times negative 2, that's totally fine. That'll be 9.55. Okay. All right, so what that means is these guys right here are going to disappear at the same rate. 5 times 10 to the negative 3. Yes, what's up? 0.935. Can I just not read my writing? Yes, it's 3.5. I know, guys. You know what? Today I deserve it. I deserve it today. Extra problem? Got it. Got it. Got it. Got it. Just because of my mistakes.
It's unacceptable.
Well, because of his mistakes, that means we should have to practice more so that.
I know. If it's this hard for me, imagine how hard it is for you guys.
Yeah.
Yeah, so you guys need to work harder. I don't know. I don't know why I'm in this class either.
Did you like that?
Which one? The one on the left, 0.065 times 10 to the negative 3. Yeah, so you just moved, that's the same thing. You just moved it over. Yeah, 7's fine as well. Yeah. Yeah, little rounding things like that's totally fine. Yes. No, I wanted to do the AP Chem. And then I didn't want to be a teacher, man. I wanted to be a pro StarCraft player or a pro League player. I could have reached my genetic potential, but I couldn't do that. Yes. All right. Exactly. Congratulations. 2 months. You're 2 months sober now, right? You've detoxed. Okay, so we're gonna do the Kc now. So the Kc is going to be equal to the equilibrium concentration. So the product 1.87 times 10 to the negative 3, and we're going to square it, divided by 0.065 times 10 to the negative 3. And again, if you have it in a different exponent, your number is going to be slightly different. As long as we're in the same ballpark, we should be fine though. Okay. Okay, so this should be your equation. Okay, and so for your final answer, dang, these problems are taking up a lot of space now. Okay, I got 51. Yes, yeah.
Like with the exponents and the independent power and all.
It honestly depends on your calculator. Some people have the times 10 to the whatever. I use E. Yeah, my calculator is E, so I just do the number. So if I did that one right there, 0.065 E negative 3. Everyone got something like that? 51 around there. Okay. Alrighty, guys. We're just gonna do more practice with this. This is pretty much all we're doing for the rest of the day. Yes. Yep. I mean, it's gonna be different situations. It gets harder. Yeah, guaranteed. Okay. 12.19. So I will give you guys a little bit of time to do this as well. Now, this one right here is with partial pressure, but it's the same thing. You can use the ice table just like how we can use it for molarity. We can also use it for partial pressure. Same thing. Okay. So I'll give you guys about 5 minutes to try that, and then we'll go over together, and I'll try not to make mistakes this time. Okay, so I set up the table for you. So just double check this is what you got, and you should get a equilibrium constant of 0.338, something around there. If you round it to 0.34, that's fine as well. You have 0.3375, that's fine as well. Anything close to that is good. Okay. You guys chilling? Chilling?
Actually doesn't get worse than that.
Oh yeah. The next problem is where it gets worse. Come on, Robbie, keep up with the program. You know by now. He's holding on to hope. You're holding on to hope that it will stay like this. All right. So up until this point, if you guys notice, we've been calculating the constants, right? Now we're going to be calculating for concentration at equilibrium, or maybe sometimes even the initial concentration. Who knows? Okay, So I'm gonna go through this one with you guys just so that we have more, I guess, just so you guys have a little more clarity. I'm gonna zoom out though, because I'm gonna need a lot of space for this problem. Okay, so if you can't see the numbers, please either squint or you can pull it up on canvas. I don't know, squinting works pretty good for me, okay? I'm squinting all the time. No, it's just my anatomy. Guys, you guys are missing the joke. Why would I be squinting? Why would I specifically be squinting? Because I have bad eyes. What are you guys laughing about?
Just like basically these.
Yeah, just start with that one. Thank you. All right, so let's start our problem. Okay, so we are gonna start with our ice table. So I'm gonna give you guys a couple minutes to make your ice table to write the equation. Again, here we are not using a real compound. We're using a generic equation for an acid, HA. Okay, and I'm gonna give you guys about 2 minutes. I want you guys to fill in the info onto the table based on the information that you have. And then after that, we'll go over just to make sure we're on the same page, and then we'll finish the rest of the problem, okay? Okay, so we are going to plug in our values from the table into our problem, okay? So it tells us the initial concentration of HA, our generic acid, is, I'm gonna do it in a different color, is 0.15 molarity. Okay, that's the only real number that we have for the ice table. So if you guys take a look at this, what's something that should stand out to you about water here? Yes, yes. Wow. You know, I wish I was that excited about chemistry. All right, no, but I'm glad to hear it. And good observation. Yes, you don't include it. We don't care about it. So you can scribble it out. You can, God bless you. You can put a sad face, you can put a smiley face, you can X it out. I would recommend not using X because we use X for the change. But yeah, cross it out somehow, okay? All right, now we are talking about this guy dissociating. So initially we'll have 0 for both of them. All right, and what we're gonna look at now is how this compound is going to dissociate. So we're going to lose our HA. We're going to gain your conjugate. And you're going to gain hydronium. Okay. So the big issue here is that we don't know the final equilibrium concentration, right? And so what we're going to do is we're just going to write it with the variable. So it's going to be 0.15 minus X. It's going to be X. And X. Oh, you guys are gonna hate this. No, we're not done. We need the concentration of the conjugate base, but we need it as a number. So math. Okay, so the only number that we have left to work with is our Ka, right? Our equilibrium constant. Okay, and that's gonna be 1.6 times 10 to the negative 2. Now, I hate working with the exponent, so if I can help it, I'd rather not use it. So you can put 0.016. Okay, and we know that that is equal to the concentration of our products. So we're going to set this up. Divided by the concentration of HA. I'll pause right there. So far, so good on this. This should be pretty familiar what we've been doing. Okay, now we're going to be plugging in what we have from the ice table into this equation. Okay, so if we take a look at the conjugate base, it's going to be X. Hydronium is also going to be X. And then down here, we're going to have 0.15 minus X. Okay, so let's simplify this equation a little bit more. So on for the numerator, we can turn this into X squared. Yeah, exactly. And you guys might be able to see what's happening or what is being formed. Okay, so we need to isolate x here. Okay, so what we're gonna do is we're gonna move the denominator to the other side. So we're gonna multiply both sides by 0.15 minus x. So on the left side, we'll get 0.016 times 0.15 minus x, and that is equal to x squared. So far, so good, everybody? The numbers are getting uglier and uglier, right? Okay, so we got to distribute. So we'll get 0.0024 minus 0.016 x. And that's equal to x squared. Isn't this amazing? It's math. This is the reason why you had to learn all this garbage. It's because we use it in chemistry.
Oh, it's only for chemistry.
Physics, things like that. Yeah, no, and you don't have to know this. I'll be straight with you. I don't think about this in my daily life, and I'm doing just fine.
You don't think about that when you're like baking? Like, oh.
Yeah, but that's more for fun. It's not like life or death. Unless you really go into industry, you're not gonna even know this.
Why are we teaching this?
I don't know. What made you sign up? All right, so if you guys take a look at it, we cannot isolate x the way it is right now, okay, because of the x squared. So what we have to do is we have to set up, maybe you know this word, a quadratic. No, okay. I know, PTSD, right? So we're gonna put everything on the same side of the equation. So I'm gonna flip it over to the other side. We're gonna have x squared. We're gonna move this to the other side. So plus 0.016x minus 0.0024 equals 0. And now we have a beautiful quadratic that we need to solve. It's already negative on the left side, so when we move it to the other side, it becomes positive. Because we got to add it. All right, so this is a quadratic, and so in order to solve it, we need the quadratic equation. Anyone? So I'm actually going to go over the quadratic formula. AP says they want the quadratic formula. That's the default way. Now, if you guys don't remember the quadratic equation, I'm going to try. This is how I learned it. To teach you with a song.
Yeah.
I'm not very musical. And I would probably mess this up because I have not done this since last year. Oh my god. I don't even have a pick anymore. Where'd my pick go? Somebody stole my pick. Okay. I don't have a pick. I'll just have to use my thumb. Please don't record me, guys. Guys, I'm gonna mess up. I haven't done this in a year. Hold up. Okay, this should work, okay? So does everybody know the song Pop Goes the Weasel?
Yes.
Dun, 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 dun. It's the same melody, and that's how you can remember the quadratic equation, okay? So I'm gonna put the I'm gonna write the quadratic equation first, and then I'll sing it, okay? So you might want to copy this down. X equals negative b plus or minus the square of b squared minus 4ac all over 2a. Okay, and the way that I learned it was to the melody of Pop Goes the Weasel. Mr. Anderson in 7th grade sang it to me, and I've never forgotten it ever since.
You should have.
Yeah, I know. But you know what? Hey, I'm gonna be honest. I'm not very musical. Disclaimer, I'll probably mess up. And if I mess up, I know I should have hired him, but oh well. You're stuck with me. Okay, you guys ready? So it's x equals negative b plus or minus the square of b squared minus 4ac all over 2a. It's out of tune, but oh well, you get the general idea, okay? No, I don't want to tune it. I've embarrassed myself enough. Of b squared minus 4ac all over 2a. Like I said, guys, I am not musically gifted. I am literally I am not. I'm very special when it comes to music. Special. Special. Do you guys want to know a funny story about medical terms?
Yeah.
So, you know how right now special is used to describe people who have special needs, right?
Yes.
Now, in the medical community before, do you guys know what the term that was used before was? It was mentally retarded. Okay? I'm sure you guys have heard that. And you heard this because in the medical community, that was how professionally you can describe somebody who, had difficulties mentally. But then people realized they can call their friends mentally retarded. And then after a couple of years, the medical community realized they can't tell a parent that your kid is mentally retarded. So they changed it to special needs. But you guys know what it was before mentally retarded? It was moronic. And so they would tell people, your kid is moronic. And that means the kid has special needs. But as you guys know, people started calling their friends morons. And so you can no longer call a kid moronic. So it started with moron to mentally retarded, and now it's special needs. And as you guys already know, in your interactions with your friends, people call each other special. They're gonna have to change it again. Anyway, that's the history of words. I know you guys are probably gonna remember that more than anything you learned in chemistry. Okay, yeah. So if we call people special enough, they're gonna have to change it more quickly. Okay. I don't know, but all I know is the next time they change it, people are gonna call their friends that too. Anyway. All right. What was I doing? Okay, quadratic formula. Quadratic formula. We're gonna put it right here. X equals negative b plus or minus the square of b squared minus 4ac all over 2a. Okay, so the way that we use the quadratic formula is that the coefficient for x squared is a. Okay, so it's the quadratic formula is formed like this: ax squared plus the coefficient for x is b, so bx minus this number by itself is c, and that's equal to 0. And so the quadratic formula allows us to take the coefficients from the quadratic and to solve for x. Okay. All right, let us do this. Okay, so x equals negative b. What's b in this quadratic? Yes. Okay, plus or minus the square root of b squared. So we're going to take 0.016 squared minus 4. Okay, what's a in our quadratic? 1. It's x squared, but the coefficient is 1. So when we plug in numbers into the quadratic, we don't plug in the x's anymore because we're solving for x. Okay, and then c is going to be negative 0. I'm running out of space. 24. Isn't this fun, guys? And that's all over 2a, which is 1. I should practice this throughout the year because I only do it once a year, so I have no idea if I even have the right chords. I'm probably singing off key. I should bring a capo or something, but anyway. Okay, so let's start simplifying our quadratic. Okay, so let's start with the easiest part, which is the bottom. 2 times 1 is 2. Good job, guys. So proud of you. No. All right, now we got to start doing the stuff underneath the square root. Okay, so let's start with our 0.016. So 0.016 squared is going to give you about 0.0002, and I'm gonna round that up to 6. Okay. So far, so good. Is she harassing you?
Yeah.
No, I'm not.
Josie, stop harassing him. Stop harassing him. All right. Next part, we're gonna do the multiplication. So we're gonna do 4 times 1 times 0.0024. Now that's negative, so that's gonna change this into a positive value. So it's going to be plus 0.0096. Everybody good with me? Following along? Okay, we're gonna add those two numbers together, 0.00026, and that's gonna give you this thingamajigger.
Is that the final answer?
Not at all. Not even close. Okay, so I'm gonna write it down here, 0.016 plus or minus. No, you're good. 0.00986.
Are you subtracting?
Hmm?
Are you subtracting?
Yeah, so we are supposed to subtract, but if you notice, our C is a negative number. So when we multiply the negatives together, it becomes plus. Yeah. All right. So this part right here, I'm gonna have to do it on this. Oh, it has exponent. Perfect. We're gonna square root that, and you're gonna get that. So if you do the square root of this value right here, you're gonna get 0.0. Let's just stop at 99. Okay. Everybody good? All right, so from here, we can go 2 different ways. Since it's plus or minus, we can either add or we can subtract, okay? But we got to do both to check our number, okay? So we're going to start with negative, how do I do negative? Oh, 0.016, and that's going to be negative. And then we're going to do addition first, so let's do plus 0.099. And that's going to give us, if we go this direction and we add it together, it's going to be 0.083 divided by 2. Okay, and if we go the subtraction route, we're going to have 0.016 negative value minus 0.099. And that's going to give us negative 0.115 divided by 2. Okay, now you can't have 2 correct answers. You can only have 1 correct answer. Okay. And these values are X. Okay, now let's go back to our ICE table, which we talked about like 20 minutes ago. Okay, because that's the original point of the question. Now, if you look at our ICE table, what unit of measurement are we talking about here?
Molarity.
Molarity. So if you notice, we can either have a positive number or a negative number, right? Can you have a negative molarity? You cannot. And so we are going to get rid of our negative number. We don't care about that guy. Sucks. It's fake. Yes.
So we're using the quadratic formula in this scenario. Can we just always assume that we're going to use the plus? For the plus or minus?
Not necessarily. Yeah.
What?
I know. Evil. Okay. So we're going to just finish it up, 0.083, and we're going to divide it by 2. And that's going to be our value for X. And we can finally answer the question that this problem was asking. The concentration of the conjugate base is 0.0415 molarity. Congratulations, guys. Isn't that so much fun?
Thank you, Mr. O.
Of course. Of course. Anything to torture you guys. Yes, that is it. All right. That was pretty much the whole class period.